So here we have question 3 of the test, the Mechanics 2011 test, and this question is about driving a metal bar into the ground. Now obviously it's to do with mechanics, so we need to use our formulas here. We've got objects that are falling, hitting other things, so it's likely that we're going to be using our momentum formula. That's going to be important. I can see something about here, average frictional force. Probably we're going to be using this over here, our work, maybe that, we'll see, but need to have those in mind. Okay, so going into the question then, we have, it says a large metal bar can be driven into the ground using a heavy falling object. So we have this in the situation shown, the object of the mass is 2 times 10 to the 3 kilograms, and the metal bar has a mass of 400 kilograms. The object strikes the bar at 6 meters per second. It comes to rest on the bar without bouncing. As a result of the collision, the bar is driven into the ground at depth of 0.5 meters. Okay, so determine the speed of the bar immediately after the object strikes. Now, whenever you have objects colliding with each other and you need to work out velocities and so forth before and after, you need to think of momentum, the conservation of momentum, because you're going to have the momentum before is going to equal the momentum after. So what is the momentum before? Well, it was this object over here. It was just there as just the instant before it struck. It was going at 6 meters per second. So it therefore, that was the object. So it's going to be 2 times 10 to the 3, 2,000 times by 6 will be the momentum before. The momentum afterwards is now they are moving together. Both this and the metal bar are moving together with a certain velocity. We want to find out what that is. So that's going to be, but now we need to add these masses because we need to have both of those. So it's 2,000 plus 400. It's going to be 2,400 times the velocity of the combination. And when we calculate that together, we get V is equal to 5. Is equal to 5 meters per second. Okay. So that's pretty straightforward. So then it says determine the average frictional force exerted by the ground on the bar. So at this situation here, as it strikes, and this is moving at 5 meters per second, it's going to drive it in a further 0.75 meters, 0.75 meters. Now, we can actually look at this in two ways. We could actually work out the deacceleration and use Newton's second law to calculate the force on it, and then use that value to find out the frictional force. Let's do it that way, and then we'll do another way also with that. So let me just bring this up here a bit so that I've got some more space to work with. Let's bring this up a bit here, like that. Actually, a little bit higher. Okay, so we know that the object is going at 5 meters per second, so its initial velocity is 5 meters per second. The final velocity would be 0 meters per second. Your acceleration is actually what we want to find, and we know the displacement is equal to 0.75 meters. So we can use that. Which formula will we use? Well, we haven't got time, so we'll need to use this formula over here. We've got V is equal to 0, so it's going to be 0 is equal to U squared. That's going to be 25 plus 2 times A, which we're trying to find, times our S, which is 0.75. So it's going to be minus 25 divided by 2 times 0.75 will give you our A. And so we calculate that. We're going to get 25 divided by 2 times 0.75, which is 1.5. and we get 16.67 meters per second to -2. It's a negative value because it's actually deaccelerating, but we're not too interested in that. We could say give the direction, but we obviously know the direction is always going to be in the opposite direction, the frictional force. So the force, the resultant force, is going to be that times the mass. So we're going to use MA. So we're going to get that value 16.67 times 2,400, because it's the whole thing, times 2,400, and we get 40,000. Now that is the resultant force that is been acting upon it. So it's going to be 40,000. But the actual, we know that this has got a force due to gravity on it already. The force due to gravity, if we use G is equal to 10, is going to be 2,400 times by 10. So that's 2,400, not that last one. So it's going to be 24,000 newtons. So to get the total force, the total resistive force, F total, would actually have to be 40,000. Why am I putting 400,000? I'm really getting my zeros mixed up here. So it's going to be 40,000. Let me just take out this one over there. Yeah, so let me just take this one over here out also. Plus our this over here, our 24,000, because the 24,000 will overcome the force due to gravity, and then 40,000 will cause the deacceleration. So the total force that will have to be applied will be 64,000 newtons. So that's one way we can do it. Now I'm actually going to do it another way also, just to talk to you about the whole idea. We can actually also use energy considerations for this. So at this situation over here, let me take this back here. Let me bring this back here. So let's just bring this back a bit here. So at this position over here, I don't know what's not working now. It's such a pain. Let's see if it'll work now. There we go. Alright, so at this position over here, if we look at energy considerations, we've got this total thing is moving down with 5 meters per second. 5 meters per second. So it's got kinetic energy. So it's got EK. I'm going to work over here. It will have EK, which is equal to a half times 2,400 times 5 squared. That's using that formula over there. Plus, it's also got some potential energy, because it's going to drop down the 0.75 meters. It's also got that amount of potential energy, so that is also the energy that's going to have to be to overcome. So that's mgh. We're going to be using our EP formula, this one over here. So the mass will be 2,400 times 10. I'm going to use 10 for gravity, times the height, which is 0.75. And that will give me, let's just work that out. We're going to get 0.5 times by 2400 times by 25 plus 2,400 times by 10 times by 0.75. Then I get 48,000 joules. Now that will be the work that the frictional force will have to do. So the force work is equal to force times the displacement. The cause, because it's working at in the same direction as the theta is going to be 0, the cos of theta is equal to 1, so we don't have to worry about that. But this is 48,000 joules of work it's going to need to do, the force, and the distance that it's going to have to do it over is 0.75. So 48,000 divided by 0.75 equals 65,000. So 64,000 newtons. So that would be a number with another way of doing it. Looking at our decimal places, here we've got 2 decimal places. Here I've got 1. Here I've got 2. Here I've got 2. I reckon probably 2 will be okay for that. 64,000 will be okay.